Just give me a second and I'll get everything set up so that we can get started on this video that we're going to take a look at for our lesson today. So we're working our way through Unit 3, which is Chapter 8, where we're looking at the systems of equations topic. And today what we're going to look at is how we would actually solve systems of equations algebraically. Our objective will be to model systems of equations, to solve them, and then to interpret them using in real life problems. And so let's take a look at what we have. Now, in terms of the vocabulary, it's exactly the same as what you had in the first lesson. We'll be using systems of linear quadratic equations and systems of quadratic equations. So first, let's review what we learned in the first lesson. It's been a long time since you took a look at that, so let's see what you remember. First of all, what is a system of equations? A system of equations is where two or more equations with the very same unknowns are together. They're interacting together, and we call this a system or a collection of the equations. What is the solution of a system? Well, if you'll remember that the first thing we learned was about solving systems of equations by graphing. And what we discovered was the solution is where the two graphs intersect one another. So we also had the two types of systems. So hopefully you'll remember this one to be the linear quadratic system. And the second one, which we also have, is the quadratic. Very simple stuff, very simple ideas. Now, we started out by first looking at what the solutions would look like if we graph things, and we looked at how many possible solutions we could have and how we would find them. We realized that in most cases we needed a graphing calculator to be able to do it accurately. And so let's take a look at what it actually would involve if we had to take a look at solving systems of equations algebraically. So let's start with a very basic idea. Here we have a system of equations, two equations with two unknowns. We've got x's and y's hanging out together in the same collection or system. Now, if you look at this one and I were to ask you what kind of system is this one, if you look at the first one, you realize it's a linear equation, and the second one is quadratic. So we're looking at a linear quadratic. Now, think about what you've done in the past when it comes to solving systems of equations algebraically. What are your strategies that you have available to be able to solve this? Well, we have something we call elimination. And elimination is where we have two equations and we force them so that at least one of the variables is exactly the same so that we can eliminate it. And when we do that, we're left with one variable. We can solve for that variable and then substitute it back in. So we're all set basically once we get going. The other option we have is something we call substitution, where we take one of the equations and rearrange it so that we know that one of the variables, for instance, in this one, the y is equal to something, and we take that and substitute it into the other equations so that essentially we're accomplishing the same thing we did before, and that is that we only have one variable, and so we can find an answer. So how does that apply when we've got a linear quadratic system going on? Well, let's first try the substitution method and see what happens. So if you look at these two, and remember this is a linear quadratic, you need to ask yourself, what's the easiest one to isolate? Now, you can isolate x's or you can isolate y's. But if you stop and consider that for a minute, hopefully it makes sense that if you're going to isolate the x, you've got to deal with an x squared eventually. And that becomes a bit of a nasty kind of thing algebraically. So probably, just being pragmatic about it, the easiest one to isolate is the y. And so let's take a look at that and go ahead and isolate this y. So if we move things around, we would actually have negative y equals 10 minus 5x. And because we'd like to get rid of so many negatives that we have hanging around, it turns into positive y, positive 5x, and negative 10. So here is what y is equal to. So now we're going to take this and substitute it in where we have the other y. So we take our equation and we plop in the one that we have, plopping it in here. And then we go ahead and distribute the negative 2 that's out in front. That would give us negative 10x, but there's a positive x here, so it's negative 9x. So we're left with a simple quadratic equation, and hopefully we can solve that. So we look at it first and ask ourselves, can we factor it? Is there something that multiplies to be 20 and adds to be negative 9? Sure enough, -4 and -5 will do it for us, which means we have two solutions, x is a 4 and x is a 5. And once we know that x is a 4 and x is a 5, then we should go back and see if we can figure out what y is. If x is a 4 and I plug it into this equation, that's telling me that y is a 10. So I've got one solution, 4 comma 10. I can also use it where x is a 5 and I plug it in and find out that in this case, the y would be a 15. So another solution, 5 comma 15. Now, we could have also tried elimination with this particular scenario. So let's see what that one would look like. So if we're going to eliminate, we're going to look at this. Think about what you have to do. Is it possible to eliminate all the x's? Not really, because this one doesn't have an x squared. So really, we're forced to eliminate the y. And so in order to do that, I'm going to need to make this guy similar to this one. And so let's go ahead and change things around. Let's multiply, in fact, by a -2, and that will make sure that the two numbers are different signs. So I take this guy and multiply by -2. And that means, of course, I multiply everything by -2. And I am left with the following equation. So now I'm going to take that equation and put it together with the 1. That's the second one. And see if I can eliminate these y's. So I add everybody together, the y's disappear. And then I have a -9x and an x squared and a -20. And if I move that -20 over, I'm left with exactly the same equation that I had when I used substitution. And then I can follow through and find my solutions. All right, so you keep in mind then that you've got two possible ways to solve these things, elimination and substitution. So let's try some of these ideas in real life problems and see how we make out. Because what we're going to have to do is take a look at what the problem is, how we might need to model something, creating the quadratics to represent them, and then solving it again. So first one we're going to do is actually just a mystery number question. Determine two integers such that the sum of the smaller number and twice the larger is 46. And also, when the square of the smaller number is decreased by 3 times the larger, the result is 93. Now, keep in mind, in this one, you are looking for integers. That means they can be positive or negative. But because they're integers, it means that they won't be a fraction or a decimal. Okay, they have to be numbers right on the mark. So, as we've said before, when it comes to mystery numbers, your job is to translate what you've been given into some kind of a mathematical equation. And so to start with, we've got two integers. One is small and one is large. So let's give them some names. Let S be the small number and L be the large number. And then we take those and think, okay, how do I translate what I've been given? So it says determine two integers such that the sum of the smaller, sum of course means to add. It's the answer when you add. So I'm going to add the smaller number and twice the larger. And that answer is 46. So I would write that S plus 2L is 46. And then let's take a look at the next one. Also, when the square of the smaller number, so that means S squared, is decreased, so subtracted by 3 times the larger, so 3L, the result is 93. And so when I go ahead and put that one down, I'm looking at this equation. So now all that remains is for me to actually solve these guys. So I take a look at them, try to make a decision on what I'm going to actually do. And let's go with elimination, I guess. And so let's try and get these guys exactly the same. I'm going to need to multiply this guy by 3 and this guy by 2. So this guy is by 3. Make sure you do it to everybody. The next one is by 2. Then we put the equations we've found together. And you'll notice that it was naturally set up so there was a plus and a minus. So again, I'm just going to add these guys. I have 2s squared, 3s, these guys disappear, and then I have this huge number. Then I'm going to need to move this around into being quadratic. Now, I thankfully can factor it. Now, you could have, you can, it's up to you really when it comes to factoring. This one might be a little tough to factor because the numbers are so large. So you might have wanted to use the quadratic formula anyway, which of course you can do. So you may choose. We get two answers. S is this number or this number. Now, if you recall, the numbers that we were being asked to find were supposed to be integers, meaning they can be negative. And they can be positive, but they cannot be decimals or fractions. So the only number we're going to use is s as a 12. And that means if we substitute it in and look for it, that our larger number is 17. So our answer is 12, 17. All right, let's take a good look at a word problem. It's actually a fairly appropriate one in some ways. It's talking about how cargo planes drop crates of emergency supplies sometimes to aid workers on the ground. So, a Canadian cargo plane drops a crate of emergency supplies to aid workers on the ground. The crate drops freely at first before a parachute opens to bring the crate gently to the ground. The crate's height, h, in meters above the ground, t seconds after leaving the aircraft, is given by the following two equations. So the first equation is when the crate is in free fall. The second one is after the parachute opens. Of course, they're not going to be the same equation. One's going faster and the other one's going slower. So how long after the crate leaves the aircraft does the parachute actually open? Well, if we think about what we're looking for here, we're looking for where these two paths of the crate are going to be exactly the same. Where do they intersect one another? So we're going to look for the intersection of these guys. So if you go back, I guess maybe let's just talk a bit for this one and say, well, what do you think you should use? Now we could use substitution. We could simply substitute in H is this one because it's set up very nicely for that. And so let's take a look at what that would look like. Substitute it in, we get the following equation. Look at that number and think 4.9. Well, I'm not going to touch that in terms of factoring. So let's use our quadratic formula. And so we use our formula, plug in our numbers. And of course, as you know, in terms of what I'd like to see that you've done, I want to see the formula. I want to see where you've plugged in the numbers, but then I'm happy to just see the answers that you come up with because I know you're putting it into your calculator. I don't need to see this in-between work, really. I look at two answers. I've got a positive number, I've got a negative number. If I think back to what I'm looking for, which is time, the negative doesn't make sense in the actual context of this scenario, so I'm going to go with this one. That my time is 3.7. So the parachute opens about 3.75 seconds after the crate leaves the plane. Second question is, what height above the ground is the crate when the parachute opens? Well, we know now when it opens, and so really all we need to do is to put in our answer for T and to be able to figure out what the actual height is. We can use it in either one, can't we? If you think about it, it's the same place, but hey, this is a much easier formula for sure. Plug it in, you find out that the height is 631. So, and it did say, the question said to round it to the nearest meter. So the crate is about 631 meters above the ground when the parachute opens. Okay, so for this part, it says, how do we solve a quadratic system of equations algebraically? So if I give you something like this, clearly they're both quadratics. What are you going to do? Well, if we consider our options, we could go with trying to eliminate or isolate for y and substitute it in, and then go ahead and figure it out. Or we could eliminate the y's. But it's always the y's you're looking at because isolating or eliminating for these x's is a little tough. You can't really get rid of your x's easily. So in terms of our approaches, we've got a couple of options, but let's go with the elimination option. So here were our equations. It's actually pretty ready for me to eliminate. I just need the signs to be opposite, but let's just go ahead and subtract to be able to do that. And so we find that 6 minus 3 is 3. 4 minus negative x is positive 5, and 4 minus 2 is 2. Here you have your quadratic. And sure enough, you can actually go through and solve this one by decomposition, because what multiplies to be negative 6 and adds to be 5? Break up your middle term, factor by grouping, you get two possible solutions. And you take each one of those, first when x is a third, and plug it in, so you get one answer. And when x is a negative 2, and you get your second answer. Okay, really, in some ways it feels different because they're both quadratic, but it's the same kind of algebra that you're doing really when it comes down to it. So what we're going to take a look at the next one actually involves an alley-oop, and just in case you've never seen it.
20 points. Let's take a look. For Matt Barr. There's the steal. Look out. Because he didn't know what he was going to do. Look, Blake said, I didn't know what you were going to do. Were you going to throw it at the backboard or what? You want to have fun. Come see summer basketball. You never know what's going to happen next.
All right, so let's take a look then at an actual word problem that involves using these kinds of motions that you have. So let's say during a basketball game, Ben makes an impressive alley-oop. From one side of the hoop, Luke lobs a perfect pass toward the basket, and this path is modeled by the following quadratic equation. Just take notice that D stands for the horizontal distance of the ball from the center of the hoop in meters, and H is the height of the ball above the floor. Then, directly across from Luke, Ben jumps up and catches the ball and tips it into the basket, and this path is modeled by the following quadratic function. You'll notice once again that D is a horizontal distance from the center of the hoop. But H this time is the height of his hands above the floor. In other words, you've got one of them throwing a ball, that's the height of the ball, the other one is the height of the hands. So the question that we're going to take a look at is, what's going to happen if we actually solve these two? Solve and interpret this system of equations. Well, here are our two equations, so we'll take them once again and try to solve them. Let's use, it looks like we're going to do it looks like we've moved things around to see what H actually is with this guy, because you've got an H by itself, and so we're going to isolate the H, and then we're going to plug them in, and we get this nice quadratic. It's a nice quadratic, but it's not easy to factor, so we're going to use our quadratic formula. Here's the formula, plug the numbers in, get our calculator. We've got two possible answers. The distance is 1.5 and the distance is 0.4. Now, remember, this distance stands for how far from the hoop they are, okay? So you've got two. For this one, your distance is the following. The height is there. And for the second one, the distance, no surprise, the height is exactly the same. We should have been able to actually predict that that was going to be the case. We've got two answers. We've got 0.4 and we've got 1.6 at a height of 3.2. So how do we interpret that? Well, the parabolic path of the ball and Ben's parabolic jump will intersect in two places, at a distance of 0.4 from the basket and 1.6 from the basket. In both cases, the height of the ball is 3.21. But do both answers fit in this scenario? Does it make sense? Well, clearly, when it is 1.6 from the basket, for most human beings, it's too far away to make an alley-oop. And so the one that makes the most sense is that Ben will complete the alley-oop if he catches the ball at a distance of 0.4 from the hoop. Okay, there you have it. We have modeled, we have solved, and we have interpreted problems involving systems of equations. So now it's time for you to practice it. So I've chosen some questions from your homework. You'll see question 3 and 4, basically just the practicing the algebra questions. Please choose 2 in each one so you can practice and, push yourself. Choose ones that are more complicated from each other, or start with the easy ones. If you need more practice, please use it. And then I've got 4 word problems for you to practice using this idea of solving systems in real life problems. Okay, so take a look at that really closely, and then we'll be getting together to talk about the homework and any problems that you had later on. So good luck, everybody. Bye for now.